Hello and welcome to Unit 5. In Unit 5, we're going to be discussing different applications of Newton's laws, with the first set being looking at forces in multiple dimensions. In this part, we're going to look at 3 examples where we have forces that do not lie strictly in the x or y coordinate system. Our first example deals with a block sliding down a frictionless ramp. The ramp makes an angle of 25 degrees with respect to the horizontal, and we want to know the block's acceleration. To begin with, I'm going to draw a picture. Here is the ramp. This angle is the 25-degree angle. For the moment, I'm just going to call it theta. Here is the block on the ramp, and it is going to accelerate down the ramp. Now, what you might think of doing is making an XY coordinate system as we normally do, where X is pointing to the right and Y is pointing upward. In this case, the acceleration points at an angle. And you would have to do, to split that acceleration into components in order to solve this problem. An easier approach is to take the coordinate system and rotate it. Let the y-axis be perpendicular to the ramp surface and the x-axis point down the ramp. Now the acceleration is again strictly in the x direction. If we think about the forces acting on it, we have a normal force. Remember, the normal force always acts perpendicular to the surface of contact. This means that the normal force is parallel to our y-axis. We also have the block's weight pulling downward, and it is not in either the x or y direction. So we need to do some work to figure out the angle that the gravitational force makes with respect to either the x or y axis, so that we can split the gravitational force into components. If we, again, I'm going to draw another picture. Here's the ramp. The x-axis is parallel to the surface, y-axis is perpendicular to it. Here's the angle theta. I'm now going to drop a line here. This line points straight down and would be parallel to our gravitational force. We have a triangle. That triangle is this one. This is a 90-degree angle. Since this is a 90-degree angle and this angle is theta, that makes this angle up here phi, where phi will equal 90 minus theta in order to get the angles of the triangle to add up to 180. I'm now going to look at another triangle. This other triangle, or more specifically, I don't even need to look at a triangle, but I'm going to look at an angle. I'm going to look at this one. This one is by definition a 90-degree angle. One side is along our x-axis, the other side is along the y-axis, which is perpendicular to the surface. If this is a 90-degree angle, and this angle phi is 90 minus theta, that means that this angle here must be theta in order for theta and phi to add up to be 90 degrees. If you look carefully, this angle theta is with respect to a line dropped straight down and the negative y-axis. So that makes this angle theta as well. I can now draw a triangle. This side is the gravitational force. This is my angle theta. This would be the y component, and this will be the x component. And notice in this case, the y component is on the side adjacent to the angle. So WEBY will equal WEB cosine of theta, and WEBX will equal WEB sine of theta. Okay. We are now in a position where we can apply Newton's second law to the motion of this block. While not necessary to solve the problem, for completeness sake, I'm going to look at the vertical direction. Remember that in this case, the net force in the y direction will equal 0 because we rotated the coordinate system so that the acceleration was only in the x direction. We have two forces in the y direction. We have the normal from the surface on the block and the y component of the block's weight. The normal points upward and therefore is positive. The y component of the block's weight points in the negative y direction, therefore I subtracted it off. This gives us that the normal between the surface and the block equals WEBY, or in other words, equals mg sine theta. Again, while this portion of the work was not necessary for this part of this, or for this particular problem, a couple of parts later, we're going to revisit the block sliding down the ramp when we involve friction. And in that case, it will be needed, and it's good for you to have seen it at least once beforehand. In the x direction, I only have one force because we are ignoring friction. That one force is the x component of the gravitational force. So mg, I wrote that wrong. The y component is found by the cosine. Yes. So mg sine theta equals max. The mass cancels, and we find that the acceleration of the block down the ramp is g sine theta. Now that we know the acceleration of the block is g sine theta, we can plug in g is 9.8 meters per second squared. The angle was 25 degrees, and that works out to give an acceleration of 4.14 meters per second squared. In the next example, we have a 60 kilogram man pushing a 45 kilogram block across a surface at constant speed. Okay, I'm going to underline that because that's a really important piece there. His arms make an angle of 25 degrees with respect to the horizontal, and we're assuming that the friction between the block and the surface is 100 newtons. What we want to find is what is the force between the block and the surface. Okay, so again, interpret this with pictures. Here's my block. Here is my man. Here is him pushing on it, and you can see his arms are not at horizontal. They are angled, and this again is that angle theta. That's that 25-degree angle. Okay. Because it's moving at constant speed, we know the acceleration is 0. Okay. Since the acceleration is 0, there is no reason not to put a standard xy coordinate system onto this motion. So let's let x be to the right and let y be upward. Okay. I can now draw the free body diagram for the block. I have the normal from the surface on the block. I have the block's weight. I have friction between the surface of the block. It points to the left because friction always works in the direction opposite of the motion. And we have the normal from the man on the block acting at our 25-degree angle. That's supposed to be a theta. It didn't turn out very well. Looking at the normal of the man on the block, here is theta. We see that the x component, said x and wrote it for the y area. We see that the y component is going to be the normal from the man on the block times the sine of our angle. And the x component will be the normal between the man and the block times the cosine of the angle. With this, I can now apply Newton's second law in both dimensions. Okay. Before I do that, I want to take a minute and identify what I'm actually trying to solve for. What is the force between the block and the surface? So my end goal is to find the normal between the surface and the block. Since that is a vertical force, I'm going to start looking at what I can find in the vertical direction. So the net force in the y direction is going to be 0 because it's not accelerating vertically. It's not accelerating at all in this question. I have 3 forces in the y direction. If we back up, we see that we have the normal that we're looking for, we have the weight downward, and we have the normal from the man on the block, the y component, also pointing downward. So when I take and write the net force in terms of my forces applied to the block, I have the normal between the surface and the block, subtracting off the block's weight, and subtracting off the normal between the man and the block y component. This means that the normal between the surface and the block will equal the weight plus the normal between the man and the block y component, which we found on the other slide to be NMB times the sine of the angle. I cannot proceed onward with this analysis at this point because I don't know this. I don't know how big the normal between the man and the block is. I don't know how hard he is pushing. To find that, I need to go look at the horizontal direction. This will also equal 0 because the block is not accelerating. In the horizontal direction, if I go back and look at my free body diagram, I have 2 forces. I have friction and I have the x component of the normal between the man and the block. I'm going to take that x component and subtract off friction because they're in opposite directions. This tells me that, wrong letter, sorry, the normal between the man and the block x component, which is found with the cosine, has to equal the friction acting on the block. Or in other words, the normal from the man on block is the friction divided by the cosine of the angle. In the problem, it was given that the friction was 100 newtons and that the angle was 25 degrees. That works out to be 110.34 newtons. Now that I know the normal from the man on the block, I can plug in numbers into the equation that I started in the y direction. The weight of the block is going to be the block's mass, which is 45 kilograms, times the acceleration due to gravity, 9.8 meters per second. And I'm going to add to that 110.34 newtons times the sine of 25 degrees. Putting that all into my calculator, I find that the normal between the surface and the block is 487.63 newtons. The last example in this part deals with a spider hanging at rest from 2 strands of web. Okay, so here is my cute little spider. You can see all 8 of his legs. Okay, we're told the left-hand web makes an angle of 30 degrees with respect to the horizontal. So here's my 30-degree angle. We're told that the right-hand web makes an angle of 45 degrees with respect to the horizontal. Okay, and we want to find the tensions in these 2 strands of web. Okay, so drawing the spider's free body diagram, we have the spider's weight, we have the tension from the right-hand web, and the tension from the left-hand web. And again, we know our 2 angles of 45 degrees and 30 degrees. I'm going to use a standard XY coordinate system again for this problem. And in this case, I have two forces I need to resolve into components. Working with the left-hand web piece first, I think I'll just use the angle in this case. I see the x component is found with a cosine because it is on the side adjacent. And the y component, which I don't have room to write, would be found with the sine. Okay. If I look at the other strand of web, the right-hand one, I see again that my y component is found with a sine, and the x component is found with the cosine. Oops. Here we go. And I really should plug in this 30-degree angle because we do have multiple angles floating around here. Okay. Also to note that this spider is hanging from rest. He's not accelerating. So at this point, I am able to apply Newton's second law. Starting with the vertical direction, I have three forces vertically. I have the two tension components acting upward, so I'm going to add them, and I'm going to subtract off the spider's weight. Again, this equals 0. The y component was TLS sine 30 for the left-hand wire, or web, and for the right-hand web, it's sine of 30. And I subtract off or set equal now to the spider's weight, which is mass times the acceleration due to gravity. And I have a 30 there where I should have a 45. Okay. Again, I can't proceed forward with this because I have two unknowns in my equation. So I'm going to go look at the horizontal direction. Horizontally, I have two forces, the two x components of the tensions. They act in opposite directions from each other. So I'm going to let the right-hand one be in the positive direction, the left-hand one be in the negative direction. Set that all equal to 0. And now I can solve for the tension in the right-hand web piece in terms of the left. So TRS will equal TLS cosine of 30 divided by cosine of 45. If you put that into your calculator, that works out to be, I'll go down here instead, 0.159 multiplied by the left-hand tension. I can now take this answer and plug it back into my y direction. So I have TLS sine of 30. Sine of 30 is 1/2. So I'm going to put that in as a 0.5. Plus TRS, which is 0.159 TLS, times the sine of 45, which is 0.71. And set that equal to the spider's mass, which is 0.005 kilograms times 9.8 meters per second squared. And now if I solve for TLS, I get TLS equals 0.08 newtons. And I can take and plug that back in and find that TRS equals 0.013 newtons. This concludes this example and this part of Unit 5.